All right, welcome everybody. I'll take my glasses off because it's right now. Next week, Ozioma Ankanqua will be here from the Division of Geriatrics and Gerontology. Rapidly becoming my favorite department. At the School of Medicine and Public Health, he's going to talk with us about the Super Agers study. He is now one of 5 international sites of the study that's headquartered out of Northwestern University. Super Agers are people over 80 with really, really good memories. They haven't called me yet for 3 reasons. In 2 weeks, Minhal Gargi from physics will be here to talk about, can X-rays trace the origins of printing? You know, and I know that Johann Gunflesch Gutenberg invented movable type in about 1450 or so. Only she's got some pretty interesting evidence that there may have been a predecessor in Korea with movable type. And she's using X-rays to figure out what kind of cool historic sleuthing can be done. So I hope you can come to that one. All right, here we go. Let's see, they can see me, I can see you. Great. Now we're going to do the more formal part.
Okay.
Great. Welcome everybody to Wednesday Night at the Lab. I'm Tom Zinnan. I work here at the UW-Madison Biotechnology Center. I also work for the Division of Extension, Wisconsin 4-H. And on behalf of those folks and our other co-organizers, PBS Wisconsin, the Wisconsin Alumni Association, and the UW-Madison Science Alliance, thanks again for coming to Wednesday Night at the Lab. We do this every Wednesday night, 50 times a year. Tonight, it's my pleasure to introduce to you Ramya Vinayak. She just coached me on how to say her name, which is great. She's a new assistant professor in the Electrical and Computer Engineering Department. I'm going to ask her the 5 questions I ask everybody. You can answer any way that you would like. Remember, it doesn't have to be true, it just has to be believable. Ramya, where were you born?
I was born in India.
Where in India?
In the southern part of India is a small town in the state called Karnataka.
Great. And then where'd you go to what we would call high school?
Yeah, so in India, we have, that is in the state that I grew up in, we have a system where 8th to 10th grade we call high school, and 11th and 12th grade we call pre-university. So before going to the university, we have like this pre-university for 2 years. So 8th to 10th, I was in a all-girls Catholic missionary school, and then 11th and 12th grade, I was in a government pre-university college, which is like a public school for 11th and 12th grade. Yeah.
Excellent. And then where'd you go for your undergrad and what did you study?
Yeah, I think I have that in my next slide. So I'm gonna try to put that in if possible.
Yeah.
Oh, okay.
Excellent.
Yeah, so I did my undergraduate studies in India. So I obtained the bachelor's degree, which is called Bachelor's of Technology in India, in Indian Institute of Technology, Madras. It's also in southern part of India in a city called Chennai.
Excellent. And then where'd you go for your advanced degrees and what did you study?
Yeah, I went to Caltech in Pasadena, California for my graduate studies. And I obtained both my master's and PhD in electrical engineering from Caltech.
And then when did you arrive here?
I arrived here in fall 2020.
Oh, there was a lot going on.
Yep.
Yeah,
it took me a year to finally see my office and meet all the wonderful people in my department and around the university. Yeah.
You are the cohort that in 30 and 35 and 40 years when you retire and you do oral histories, that's going to be an amazing story to tell. Tonight you're going to talk with us about learning from societal data. Would you please join me in welcoming Ramya Vinayak to Wednesday Night at the Lab?
Thank you. Thank you. Hi, everyone. I'm really delighted to be here. As in the introduction, we talked about, like, you know, I grew up in India, so I'm here, moved here around 10 years ago to start my graduate studies, which was on the West Coast. I also spent around 3 years in Seattle as a postdoctoral fellow So Madison was my first experience when I moved here with a place with all seasons, and so far I've been enjoying it, and I've survived 2 winters. And I've realized that I like sunshine a lot, even if it is freezing, because I think the time in Caltech was sunny California. I didn't realize how much I was relying on sunshine. Then I spent 3 years in Seattle. Amazing summers, but very, very, very cloudy, like 9 months of the year.
Yes.
A beautiful city, but made me realize how much sunshine matters to me. Yeah, I'm really glad to be here and interacting with you all. I am used to, like most academics, giving a lot of research talks to technical audience. So this is going to be my first attempt to talk about my research to a more broader public audience. And so please feel free to kind of stop me and ask any clarification questions if there is something super unclear as we are going forward, because my goal is to try and together kind of understand some of the things that I'm super excited about. And hopefully by the end of the talk, you will have a better idea about like what machine learning is and what these machine learning algorithms at a high level do. And if there are any more discussion kind of questions, maybe we can take them at the end, because we'll have some Q&A, and I'll also be happy to come to the library with I think there is folks are going to go to libraries, what Tom said. So yeah, I'll be happy to also engage in more discussions over beer later. Okay, so here's the outline of the talk. So I'm going to start with some broad introduction to machine learning, and then later move to questions related to the challenges that arise when we are trying to learn from societal data and how we can go about addressing those challenges. So that bit is what going to be giving some glimpse of what research focuses, the research focus that I have in my lab here at UW-Madison. But I think it would be good to kind of go through the outline so that we can all be on the same page in terms of what machine learning is and what do these systems actually do, how do they actually learn. So at a high level, machine learning refers to the process of using large number of observations to discover some underlying patterns, right? So you have some raw data, and what machine learning attempts to do is to find some underlying pattern. So the assumption here is that there is some pattern in the data, because if there is no pattern in the data, then there's not really any pattern to really discover. But assuming there is some pattern in the data, we want the machines to be able to discover them. For example, if you think about object detection in images, using lots and lots of examples of images with labels of objects in them, we hope that we can teach machines to identify objects in new images that they have not seen before. So how are these machine learning algorithms different from computer algorithms that we are kind of familiar with, like the softwares that we use on our computers, on our personal computers, right? So typically, computers need instructions on what to do with the inputs that they're getting, right? For example, say we want a computer to sort a bunch of numbers for us. So I give it an input, a set of numbers, and I want it to give me an ascending order of those numbers. What we do is just give a set of instructions to the computers, which are called algorithms, so that the computer knows what to do with the input in order to produce the output that I desire, right? So that's the typical computer algorithms. So machine learning algorithms are also algorithms, but they are slightly different from general computer algorithms. So let me give you another example to kind of illustrate the difference. Let's say we want to distinguish apples from oranges. Okay, so this is a cartoon example. So let's say for every fruit, I have a feature of just 2 dimensions. So I have the ability to measure its color, and I can also measure its taste. And I want to be able to decide whether it's an apple or an orange by using these 2 features. Suppose this is how they kind of lie on this 2-dimensional space. The x-axis, let's say, is color, the y-axis taste, and there is this like green line that above that it's oranges and below that it's apples, right? So if I want a computer, without looking at the pictures, but only using the features, be able to identify whether the fruit is an apple or an orange, I'd have to tell what to do with the features. So let's say, this line, I can mathematically write down what that line is. There's an equation I can write down. And the instruction is going to be something like, plug in this equation with the features of the fruit that was input. And if the value that you see is bigger than some threshold, which would mean that this lies above the line, then declare that it's an orange. And if it lies below the line, then declare that it is an apple. And so this is what a programmer would do if it was a hard-coded algorithm that we tell the computer exactly what to do with the input. However, what happens in many situations is that we a priori don't really know how to set those A, B, C, and eta, those parameters that is defining this line. It can be also situations where we might have more complicated data, right? We might have data in much higher dimensions, which is not easy to just visualize for us to see that there is a nice line that might be separating the data. And also, the separators need not be, something as simple as a line. The surfaces that separate these things out might be a bit more complicated. And so what we want to have is the ability to let the machine itself figure out what this separator is by providing it lots and lots of examples. So that's where machine learning algorithms kind of differ from the general algorithms, is that instead of hard coding these parameters as a programmer, now we're going to let the machine figure out what those parameters are by using a bunch of data. So I have now, all these question marks are the parameters I want the machine to learn. And we will provide it lots of examples, lots of fruits with their features, but also its labels, whether the fruit was an apple or an orange, etc. And then we will let the machine learn. So it has, I also have to kind of tell it like what kind of function to learn. So let's say I tell it that learn a line. I'm not telling which line, but I'm telling it learn a line. So it's going to learn the parameters so that it kind of finally figures out that it's this green line above which it's oranges, below which it's apples, right? So let's see another example that we are all very familiar with. So this is again another example of what's called supervised learning. We all use email clients, right? So we get lots of emails every day, and the email clients are pretty smart that they figure out which emails are important and they put them in our inboxes, and which emails are spam and put it in spam. Sometimes they make mistakes, but if you compare what they were probably 25, 30 years ago, they have become much, much better now in identifying spam, right? So how do they do that? One way to go about it is, I as a programmer can try and list all possible rules that I can come up with so that I can tell the machine exactly what to do when an email arrives. That maybe if the email has certain number of exclamation points, or there's some dollar signs or some links or something, come up with these rules like, oh, if this is the case, then classify these emails as spam, otherwise not spam, and so on. But the problem is there can be so many exceptions to those rules. And the other thing is, it's also really difficult to think about all possible rules that I can come up with. So this is another case where we would want the machine to ideally figure out what is the rules to kind of classify emails as spam or not spam. So what we do then is to train a model. So by using lots of labeled data. So what do I mean by labeled data? We will provide the machine lots and lots of emails. And along with that, I'll also tell it which of these emails is spam and which of these emails is not spam, right? So the green boxes are not spam emails. So important emails, they should come into my inbox. And the red boxes are the emails that are spams and they should go to spam folder. So I'm giving these examples and let the machine learn what features are important, what features are not important, and then figure out how to classify them so that when the new unseen email comes, it can automatically classify it as either spam or not. So again, the main thing to remember about machine learning algorithms is that unlike general computer algorithms, instead of predefining certain rules as to what to do with the input, we are letting the machine figure out what are the important features, etc., so that it learns what to do with the input to provide the kind of output we want. Now, the example that I showed you so far belong to a class of problems called supervised learning problems. There, the supervision was coming from the labels that I was providing in the data, but you could also have pattern recognition or machine learning questions that arise when you have unlabeled data, and we call it unsupervised learning. And let me give you a couple of examples for these. Let's say a social media company is really interested in trying to identify different subgroups of people. And in each groups of people, they kind of want to put together people who share common interests. This can be useful, for example, to provide better recommendations, etc. So typically, you can model some of this data as graphs, where each node is an individual, and the link between the individuals tells us whether they're friends or not friends, whether they're connected in the social network or not. And then we are not necessarily going to have information about who is in which group or not. So we don't have labels, we just know the nodes and their connections. And we want to let the machine try to figure out, can you find groups of nodes that share lots of connections among themselves? That is, groups of individuals who share lots of connections among themselves compared to the connections that go outside the group. Right? So this way you can group these individuals together, and we call it cluster. So you're clustering the nodes in this graph, and that's an example of unsupervised learning. And this can be helpful in many other domains as well. For example, in biology, there are data sets that can be modeled as graphs as well. For example, protein-protein interaction networks, where nodes are the proteins in the graph, and the links tell us something about how these proteins are related. And biologists often use clustering techniques to kind of figure out which groups of proteins are important for certain functions in our bodies. And so it can be very, very helpful to really identify these patterns that exist in the data, even when there is no labels attached. So unsupervised learning is also very useful in discovering patterns in the data. Clustering is not the only type of unsupervised learning. There are many more. And one of the other unsupervised learning that's very, very common is what is called density estimation or learning distributions of something. For example, let's say there is lots of, we have these fruits which have different flavors. I've really simplified it in a cartoonish way that there's just this sweet or sour. That's the taste parameter that I can learn. And I'm interested in trying to understand what is the distribution of this flavor profile look like. Right? So there might be some underlying distribution that there's a bunch of fruits that are mostly sour. Maybe there's a lot more fruits that are sweet, and then in between there might be a little few which are kind of sweetish and sourish. But there might be certain distribution of this flavor. It might need not be flat. It could be some other shape. I don't know. And I want to really learn, is there a nice shape there, or is it actually just flat? Or is it just one type of flavor that all fruits have the same flavor? So we don't know this underlying distribution, but what we have access to is samples, right? I can just go and collect lots of fruits, and I can measure their taste. And I can use this sample that I'm here denoting by these gray dots to try to figure out what might be the shape of the underlying distribution of the taste. Right? So this is also unsupervised and learning these kind of like distributions can be really helpful in downstream tasks. Usually what we do is we kind of mathematically model these underlying distributions with some functions. And these functions are also generally parameterized by certain parameters and denoting here by theta. And when we say you are learning the underlying distribution, what we essentially mean is that we are providing lots of samples to the algorithm so that it can learn those parameters theta that will then tell me what is the underlying distribution. Right? So this is at a high level, like what like machine learning algorithms try to do. There's also another type of learning called reinforcement learning that is related to kind of dynamic, like action, like reaction, and you are learning over time. But I'm not going to kind of go over that in this talk, but I'm happy to kind of discuss about it later. But are there any questions so far?
So, do any of these so far help us with voice recognition?
Yeah, so actually, that's so it's most of the time you can be using supervised learning if you want to really identify specific people's voice. But unsupervised learning can be very helpful in maybe learning a good prior over the population so that you could potentially do better by kind of leveraging the prior. So you can be using mixture of both supervised and unsupervised techniques. But if you want to recognize individual people's voice, then you would need to also provide the labels of whose voice it is. But if it is only about just identifying the speech patterns, right? So then also you're kind of doing like, or rather if you're trying to figure out what did I say, right? The words I'm saying. There, again, you don't have labels in terms of whose voice it is, but you need to have some transcripts. You need to provide some examples of like audio, what was the audio, and then you have to also provide some transcripts so that it can learn. So it will be supervised learning.
So that's the kind of thing that's helping with the subscripts coming through right now.
Yeah. So far, I kind of told you what machine learning is, but how do these machines actually learn? Okay, I told you that they can learn using data, but how do they learn? So when we say how machines learn, I think maybe we can also repose that question as how are the parameters of those functions, that the way we are modeling these things as functions, so how are they learning those parameters? Whether it is supervised learning or unsupervised learning, typically what we do is that we provide the machines not only data, but we also provide it a recipe. So machine learning algorithms are also algorithms. So we are still providing the computer some instructions, but those instructions are more about what to do with the data so that the machine can learn. Right? So typically what we do is we define something called a loss function, a loss. So if let's say the machine uses some function f theta to classify apples and oranges, in that apples and oranges example that we will look at. If it makes a mistake, we want to tell it like how much penalty does it incur when it makes a mistake, right? Then you kind of average this loss over all the data points it is using to learn. So that will be kind of overall how much penalty did it incur. And what we are telling the machine to do is to minimize this average loss. So the recipe is that the machine has to search over lots and lots of functions to find a function that has very little loss on the data that we are trying to train it on. And our hope is that if we can find such a function, that it could potentially generalize and work on uncertainty. So I'll talk a little bit about that later, but basically the recipe is what we call an optimization problem. So we have to tell the machine what is the penalty when it makes a mistake, and how do you aggregate that penalty over all the data, the entire population of the data that it is learning on. And we're telling it to minimize that loss. And I'm also telling it what class of functions to search over, because we can't tell a machine to go search all possible functions. right? So that would be too much. So we also specify to it some class of functions to search over. And once we specify these things, we provide this recipe. We also provide data. Then the machine learning algorithm goes about learning. Some of you might be more familiar with a different way of looking at this, where instead of minimizing the loss, you might be maximizing what is called the likelihood of the data. So another way to think about this is that the underlying parameters, if you had generated data from that, what would that data look like, and how far away is the data that you saw from that, right? And then you can kind of define a way of saying how good is your guess, and then you can maximize the likelihood. If this can be equivalent to minimizing the negative of that likelihood, so don't kind of attach too much about maximizing, minimizing. This is an optimization problem at the end of the day, where I have an objective. My objective is to either minimize the average loss or maximize the average likelihood. And so I need to also provide a recipe of like how do you search over the function space to arrive at a good solution. And thankfully, we have colleagues in optimization who have worked for very hard for several decades and have given us really amazing algorithms to do optimization. So what we do is to define these things and then use optimization techniques to do optimization. Right. So this is how actually machine learning algorithms learn. So it's not just the data. So we can't just throw data at the machine and say go learn. There's a lot of choices we are making in terms of how we are defining loss function, how we are telling it to aggregate the loss function over the population, right? So there's a lot more than just data to learning from data. So if we go back to this spam classification example, we can now write a kind of a flow chart. So there is some unknown target function that is really like, that says that, there's unknown real function that can classify the email as spam or not spam that we don't know. But we get samples and then we input that sample into the machine learning algorithm. We also tell the machine learning algorithm what space of functions to search over, and then it spits out a hypothesis that it thinks is close enough to the truth. And the way it will measure how close to the truth is saying how well did you do on the training data that you gave. Typically what we do is we take a subset of that data and consider it as test data. So we don't show that subset of the data to the algorithm, and we let it train on the rest of the data, and we measure how well can it predict the small subset of the data that we set aside ahead of time. And that gives us some cue as to is it really learning. Because our goal is not that it should do really well on the data that we have already shown to it. We want it to do well on unseen data when we deploy these things. Okay, so that brings us to this question: is why should we care about understanding these, right? So machine learning for data-driven policy making and decision making is really becoming ubiquitous in lots of domains. So it's not only about having apps on our phones that can help us identify objects, or if I go on a hike and I see a tree, I want to identify it, I take a picture and it tells me what tree it is. It's cool, that's nice, but if it makes a mistake there, assuming that I don't go about eating the berries from that tree, it's okay, right? If it makes a mistake. But if you're using this system to make a diagnosis of what medical condition a patient might have, or use it to make a decision on what kind of treatment we should provide to a patient, the stakes are much higher as to what making a mistake would be, right? So I think we should really care about trying to understand when these algorithms work, when do they fail, so that we can have the trust that in whether we should be able to use them in critical applications or not. For example, these data-driven techniques can be very helpful for us to also take policy decisions. for example, should we provide free flu vaccines to everybody in the state of Wisconsin? And say we have come up with that policy and we go ahead and do that, and then we want to assess was it effective or not, right? So we can actually use data-driven techniques to kind of answer lots of these questions, but it's also very important for us to understand what are those techniques actually doing? Are they really working the way we expect them to work? So now I want to revisit this question of like what is finding a good function means? What does it mean to really learn? Is that what we really want is to find some hypothesis function that can predict well on unseen data, right? So the blue points and the purple points here in this figure are the ones that I've seen, and that's what the machine is like kind of using to learn that green line. And our real hope is that when those gray dots show up, that that the gray dots above that line are actually blue and the gray dots below the line are actually purple, right? Like we want that to be the case. But the way we are going to do this, what we are actually doing is this optimization, right? What we are doing is minimizing this average or error on the observed data, and we are hoping that the error on the observed data gives us some indication of what the error would be on unseen data. So this thing is called generalization. This is a technical term that gets used in machine learning. And then the hope is that we can generalize from this training to unseen data. And a key assumption that goes into guaranteeing these, at least for a lot of the algorithms out there, is that the data we learned on and the new data are coming from the same distribution. So if this assumption does not hold good, then we can't guarantee generalization in many scenarios, and that leads to problems when we try to deploy machine learning algorithms in the real world setting. So what can go wrong? So this is an article that came in ProPublica in 2016, where they analyzed like a system, like an algorithm that criminal justice systems were using in order to decide who gets parole and who doesn't, right? Like there was a system that was giving scores to offenders as to whether they were high risk of reoffending or like low risk of. And what the analysis showed is that it had a lot of bias based on the race of the offender. And it was, when it made a mistake, it was making mistake in different ways for different races, right? So what they found is that when the algorithm labeled somebody high risk, but it turned out that they didn't reoffend. If you look at the percentages, that happening when the offender was white was around 24%, but it was roughly 45% when the offender was black, right? And the opposite kind of mistake was happening in the opposite way, right? When the machine labeled somebody as low risk, the chance of like them actually going and reoffending, it was higher for offenders who were white than offenders who were black. So in a way, systematically, it was giving higher scores to offenders who were black, even though a lot of them, in hindsight, when they did the analysis, they had tracked them for a few years. It turned out that many of them didn't really reoffend, right? Like so, even so, if we just look at average loss over the whole population, we might not be able to kind of tease this apart. And sometimes it's also critical for us to remember that we're making the choices of what loss functions to use, how to aggregate it over the population, and so on. And so even if an algorithm looks like it is having certain like low error rate, it is important for us to still think about like if our data, if we are applying it to a group, a population that has lots of different subgroups, and especially in kind of domains where we know that there has been historically a lot of bias in the system, and we are using historical data to kind of learn a lot of these things. There can be multiple sources through which biases could be occurring, and machine learning algorithms can really amplify this a lot, right? Yeah.
Good question. So I think I may have seen this somewhere. Was race identity part of the input factor? Or can we just exclude that completely and throw them all?
That's a good question. Actually, even if you remove weight, that's not really sufficient because there is enough things in the rest of the features that we can recover race from, right? So, for example, if you just have where the person lives, their zip code, like the way we live, is pretty segregated, right? Like, so if you tell the zip code of where the person comes from, with very high likelihood, you can kind of say what race they could be from, or if you know which high school they went to. And so there's lots and lots of information in the data that's very correlated with each other. So by removing one feature, we will not be able to kind of take away that. So it's there's a lot more nuance that goes into this. But that's a very good question. Yeah. But so essentially, this is one of the things I wanted to point out is that a lot can go wrong with machine learning algorithms. And there's like many examples of this that we show. So this is not an exhaustive list, but many systems, many algorithms that technology companies have been using are rife with different kinds of biases. So again, going back to this what we really want is to predict well on unseen data, but we are trying to find our hypotheses by minimizing some average loss, right? And so there could be issues arising from this choice that we are making in how we are penalizing the algorithm when it makes a mistake. And there is another aspect is that this assumption that the data we learned on and the data that we will see in the real world are coming from the same distribution, that might not hold good in lots of real scenarios. So it's important for us to then kind of think about how do we want to design our algorithms to work in scenarios where you might have subgroups in your population, and the way these algorithms might be working might have to be sensitive to that. So then generally using a recipe that was okay enough for identifying, which tree it is when I take a picture, maybe that might not be necessarily the best way to go. That might not be the right recipe to use when we're trying to teach machines to do different tasks, right? If our algorithms are really relying a lot on the distributions of the new data and the data we are learning on to be exactly the same a lot, and they're super sensitive to that, then we will also be in trouble because in real life, that's not going to happen because we are learning on some curated data and that might not really match exactly what we will see in the real world. And so we want methods that can be a little more robust to this, that we shouldn't be really sensitive to that. So to make machine learning algorithms work, we of course need some software engineering, like code, and we need to experiment on the data. But it's also very important to kind of think about mathematical foundations behind it to kind of understand how should we design these algorithms, how should we test these algorithms, and how should we measure the performance of these algorithms, right? So things like if you have a machine learning algorithm, when does it work? What properties does the data need to have in order for it to really work, right? How much data does it need in order to really learn? And another way, like how well can we learn with given data? So really understanding these things become critical. And there's lots of different mathematical tools that go into building this mathematical foundation. So probably in statistics, linear algebra, optimization, signal processing, image processing, information theory, and a lot of really great mathematical tools that is available for us can be used to model and understand these scenarios. So at UW Madison, so you will find faculty who are doing machine learning research that is spread across lots of different departments. Right? So I'm in PCE, I'm also affiliated in computer science. I've collaborators in statistics, in math, in industrial systems engineering, and also lots of collaborators in domain-specific areas, because it does become important to take and collaborate with the domain experts to figure out what's the right thing to do in a specific domain. Right? Something that's like good for healthcare scenarios might not necessarily be good for, identifying cats and dogs, right? And so domain expertise really becomes important, and so kind of collaboration across departments, I think is important. And the other thing that that we need also for the public to kind of like be aware of how these algorithms like roughly work, and like where are they getting used, because this is like a new territory for us, right? Like so before we can use these algorithms for really critical applications, I think it's also important that not only should it be researchers and engineers and technologists and domain experts who kind of have to give input, but also we need to understand like what should we value in these systems, right? Like if you're using these systems in critical applications, like if they make mistakes, what is the kind of like accountability we want to build in around this? How do we ensure that these systems are fair? Are they transparent? Can we audit them? And all of these things, I think, should involve general public, and it shouldn't be decided only by engineers and researchers and technologists in the area. So I'm hoping that at least like that we get like more and more involvement of public in and how these algorithms are going to affect our lives. And in the remaining part of the time, I want to give you a little bit of a glimpse of what challenges we actually face when we are learning from societal data, and how we can go about addressing it. And I'll provide some examples of some of the works that I have done in the past and that I'm currently doing here at UW-Madison in my lab. So if we visit the machine learning system path, here's a kind of a block diagram of what it looks like. There is some data, there is the machine learning system that takes in the data, and it provides some kind of inference as an output. And that inference can be, this output can be used by domain experts or policymakers to make some decisions, or like use it to kind of make some scientific discovery, or like, so there is some further downstream things that could be happening that is a function of the output of this machine learning algorithm. So usually, sometimes we hear this garbage in, garbage out, right? Like, so yes, if I input data that is really like not of good quality, or it doesn't have any pattern in it, I can't really expect that machine learning algorithm will magically find something useful, right? That's true. But the reality is a little bit more nuanced than just this. Right? So if you think about where the data comes from, of course, depending on the application, the source of the data can be very different. In the applications that I am really intrigued by, or I care about, in those applications, data comes from people. For example, if it's healthcare or social sciences, psychology, and so on. And when we have data that comes from people, there's a lot of heterogeneity in that data. And that is something that we should be careful about. So if you think about the kind of spectrum, like I like to think about it as a spectrum of like how we obtain data in the first place. There's varying level of control we might have in how we obtain the data that we feed into the machine learning algorithm. On one end, we have observational data. Right? So we have the collaborators who have already collected data, and we want to kind of try to use that data to find some patterns. Okay? So I don't have much control over there, like how the data gets collected. On the other end, there are situations where I could have the ability to go and elicit data. I think about like, surveys. Right? If we, if a new survey is about to be conducted, then we can think about like what kind of questions should we ask? Like how should we try to collect this data so that we can get quality data that we can use for further downstream analysis, right? So there is a spectrum of that control that we can have. And depending on where you lie in the spectrum, there's different kinds of challenges and opportunities that come for learning from data. So in the observational setting, for example, in social sciences, in epidemiology and health sciences, typically you have data that has been collected over a population. And the key challenges in this setting is the heterogeneity in the data. So people can be of different places, ethnicities, genders, they could be having different socioeconomic backgrounds, and all of these things could be affecting the outcome differently depending on what you're trying to study, right? And the other thing is that the issue of small samples or small data ranging. So even if you have a very large cohort that is involved in the study, sometimes we have very little observations per individual in the study. So it's very difficult to say something very precisely about an individual, but there's still some scope of maintaining some sort of like semblance of keeping the heterogeneity, right? Because we don't want to completely wash away the heterogeneity, but by averaging over everybody. On the other hand, they have too little data to say something very specific about an individual. So there's the question of what can we do in between that is still useful, right? So how can we make reliable inferences in these situations? The other setting is where we could go and collect data, and there's lots of different ways to do it. There are platforms like Amazon Mechanical Turk that allows you to collect data. We could also be conducting surveys, and there are like studies that have participants coming into the lab, and they'll be getting involved in the experiments, and then we'll be collecting data and so on. So there's lots of different ways we could be collecting data. The challenges that come in this setting is that typically there is some noise in the data that we collect. And also there's always cost associated with collecting that data, right? So, in surveys or, in studies where we are getting the participants to come and participate in the survey, it's a lot of like both in terms of like cost it could be the monetary or it could be the time that it takes to actually collect the data. So in this setting, the questions of interest is how do we go about obtaining quality data that is required to make reliable inferences, but we also want to do it in such a way that we can be under the budgets that we have, right? So my research kind of focuses on both of these aspects, but today I'll like in the next few slides I'll give a glimpse of how to address the challenges in the first one, the one when you have like societal data. And before I do that, so my research mainly focuses on developing theoretically grounded machine learning tools so that we can make reliable inferences from data that comes from people. And I do this by both looking at theory and applications. So I look at both algorithms and analyze the algorithms to understand when they work, when they don't work, trying to kind of understand like the limits of these problems, like how best can we even aim to do in certain scenarios, and then try to understand how far are we with the algorithms we have and how can we do better and questions like that. And I also collaborate with domain experts on applications so that we can take these algorithms and insights that we obtain from theoretical analysis and apply them to domains. And many times while doing so, we face a lot of challenges because it's very unlikely that off the shelf something will generate that as a general algorithm will immediately work on specific domains. So I really enjoy collaborating with domain experts because it also, apart from the joy of seeing something applied in specific domains, it also provides me new challenges to think about, to go back to the whiteboard and try to think about like how do we solve those problems. Here's one of the examples of the research project that I worked on during my postdoc. Let's say we have a large random subset of population in Wisconsin, and we are trying to understand the likelihood of people catching flu, right? So let's say we have observation for the last 5 years for the randomly chosen samples of people, we know whether they caught the flu or not over the last 5 years. So each person, so the model here is that each person has some probability of catching the flu that I don't know. All I can observe is whether they caught the flu or not over the last 5 years. So what we can model this as a coin, like if I had a coin that has a certain bias, I don't know what's the bias. What's the bias of a coin is the probability of it landing heads when I toss it, right? So, if it need not be fair coin, so it could be biased, but I don't know what that bias is. But if I only see 5 tosses of that coin, it's very difficult for me to estimate what is the bias. Because when we do these kind of estimations, there's always some uncertainty. And with 5 tosses, if I calculate what my uncertainty is, it's very bad, right? So if I want to really kind of like estimate what is the probability of each individual catching the flu, that is going to be really bad because I don't have enough data to do that. But can I learn the distribution of the probabilities over the population? So maybe that can help me to understand a little bit, gain a little bit more insight into what might be the general probability of people catching the flu, and why would that be helpful? If I can do that, it can be helpful in downstream analysis, right? So I can use this underlying distribution to kind of do testing, like is it unimodal or bimodal, right? Does everyone have the same probability of catching the flu? Or are there actually subpopulations that have more chances of catching the flu, and there may be some other subpopulation that has less probability of catching the flu? It can be helpful in estimating certain properties. For example, a policymaker might be interested in knowing what is the fraction of the population that have more than 50% chance of catching the flu. Right? If it is bigger than a certain proportion, maybe they want to take certain intervention steps ahead of time. And so, like estimating these properties can be made possible by learning the underlying distribution. And it can be used as a prior for many other downstream tasks. So this is a problem that that arises in many domains. And if we look at the history of this problem, in 1960s, Frederick Lord was studying this in the context of psychological testing. So here's the setting that Lord was interested in. There is a study that involves tens of thousands of individuals. Everybody has something called a true score. So this is the probability with which they give an answer correctly to a question. Everybody is given a test with 10 questions, and the goal is, given the scores on this test, estimating or learning the distribution of the true scores. So it's not a wonder that Frederick Lord was working with education and testing services, so he was really interested in this problem in the 60s. And you can mathematically model both of these problems in the very similar way. So I'm not going into the details of that, but what I want to highlight is the issue that we have with the small data per individual. So what I'm plotting here is what is called a cumulative distribution function. So you don't need to know what that actually means. But what I want you to focus on is that the black curve that you're seeing, that's in this simulation, that's the true underlying distribution of probabilities. It is just saying that I'm in a simulation, I can create the data. So what I did is I just created a lot of like fair coins. So all the coins are just fair, right? So it's just all like 0.5, right? And then I take 10,000 such coins and I toss each of those coins 5 times. And then I want to kind of estimate what is the distribution of the biases of these coins. So if I go the naive way of just looking at the empirical, distribution or the histogram of what I observe, the red dotted line is what I observe. It's very bad estimation of that black curve, right? And so we can wonder that maybe 10,000 coins was not enough. So the population size maybe that I used was not enough. What if I had more coins? Would that help, right? So then the plotted, the answer is no. And the plotted also like curves here, so that you can see The answer is no, because I'm still constrained by the fact that I have only 5 tosses per coin. So it is not that 10,000 coins are not enough. Doesn't matter if I have 1 million or 100 million coins. I'm still constrained by the fact that I can see only 5 tosses per coin. So small data regime does really pose a lot of challenges when we are trying to learn from it. So instead of like doing the naive empirical estimate, what we can do is do this likelihood thing that I talked about early on. And in fact, this is a method that has been used in this setting. Again, going back to Frederick Lord, few years after he first started looking at this problem, he started thinking about using this likelihood method. So what was not known for a very long time is how well does the MLE actually recover the underlying distribution, right? Is it any better than that naive way of like doing the empirical histogram or not? Are there better algorithms out there? Should we be searching for better algorithms that will learn even better in this setting? And so along with my collaborators, a few years ago, what we showed is that MLE, of course, like in fact, does much better than the empirical estimate. Not only that, but it's optimal. So that there is no other algorithm out there that could uniformly do better than this maximum likelihood estimator, the likelihood maximizing the likelihood. And this kind of setting arises in many applications. So I collaborated with biostatisticians where we were looking at data that comes from single cell genomics. So there's lots of advances that have occurred in biology where we've been able to now measure things at single cell level. And so it really gives a lot of opportunity to kind of develop tools and techniques to kind of tease apart lots of patterns that previously we could not have. And so we developed certain statistical tests based on learning these underlying distributions over the cells. Now the population now is the population of cells, and you can model this as a slightly differently, but I'm not going to go into the mathematical details. But you can use these underlying distributions to build tests on that, so that is another example. I will conclude with a few slides of some ongoing research. So I've been interested in learning preference learning. So preference learning is a setting where we want to kind of understand how we make judgments of what we prefer and what we don't prefer, right? Why do we care about this? Because this is really on scientific level really interesting from like cognitive and behavioral sciences point of view. I have collaborators here in psychology who was really interested in understanding how do we represent different concepts and items and values, and how do we make judgments based on that, right? It's also really interesting in other domains like social sciences, because we are really interested usually in collecting survey data and trying to kind of gauge what people want and where is this, like, what is the society valuing in certain stages. Pollsters are really interested in it because they really want to estimate what people think about different issues. And also commercial sector is really interested in it because companies really want to recommend things better and do better advertising, and they're always interested in trying to understand what do people prefer in terms of, like, whether it is buying items on an e-commerce platform or watching movies on a streaming platform. So there's lots and lots of like reasons why we care about preference learning. And typically how it is modeled is that there is some space in which you can say represent different groups. And there is some, I am this blue dot, I have some ideal preference state. So how much I like a specific fruit is kind of a function of how far away that flavor is from my ideal preference, right? So typically what we could do is ask people questions like, which one do you like better? Do you like, grape better or watermelon better? And using these questions, we can try to infer what that ideal point is. So that what is the problem with the existing, or the more than problem, what is the limitation of the existing models and algorithms is that it's often kind of universal. So it's kind of difficult to ask too many questions to an individual. So what we usually do is to just take everybody's data together and just learn a preference point. But people have diverse tastes, right? And so my preference in taste of fruit is not going to match yours, and that need not match wrong. But if I want to individually learn the preferences, I would need to ask lots and lots and lots of these kind of comparison questions to people. So that might be too much to obtain in terms of both cost and also the cognitive overload, right? Like, what's your name?
D.
D. If I want like D to come sit and like take 2 hours to kind of ask lots and lots of like diverse questions to figure out what her preferences are, that can be very tedious too. So instead, the question that I'm really interested in trying to think about, okay, I don't necessarily care in many cases to really learn an individual's preference really, really well, but I might be interested in just knowing what's the taste profile of people in Wisconsin look like, right? So I might be just interested in learning the distribution over the preferences rather than learning individual preferences. And maybe, this can be useful in lots of different ways. For example, I might figure out that, oh, there is a space where people who this looks like lots of people have some preference of that taste, but there is no product with that flavor. So maybe as a commercial entity, I might be interested in coming up with a product there. Right? So there's I might be just sociologically very interested in trying to understand, oh, how does the taste profile of people in Wisconsin differ from people in Massachusetts? Right. So there's lots of questions that you can answer by learning the underlying distribution. So the question I'm really interested in is, can we actually do this? Can we learn these preferences with, say, just one measurement? Like I'll just ask one question per individual and can I go about learning this? There's some recent results, some progress in some specific settings. I'm really intrigued and interested in understanding when we can do this and how well can we do this. And I have collaborators in psychology here at UW-Madison that I'm collaborating with, along with my colleagues in ECE, to kind of understand broader sets of questions related to this. And another ongoing collaboration I have is with cardiovascular experts at the Department of Medicine here at UW-Madison. And what we are really interested in understanding is how do we try to learn models that can be helpful in prediction when we have diverse set of people that is involved in the data. So these are the situations where a single model might not predict the chances of a disease for the entire population. There could be different models that work better for different subgroups. But the problem is, a priori, many times we don't know these subgroups. They're not as simple as like, oh, just the, is it for all the people of like certain races, maybe some things might be true or not. But it can be a lot more complicated. There could be things related to the medical history or like the gene sequencing. Like there's lots of different things that could be playing their role. And so these subgroups might not be very easy to define ahead of time. And when we are in such scenarios, how do I simultaneously learn the subgroups as well as learn the models that work well on the subgroups? So there's questions both on the theoretical front that I'm really excited about, and on the practical front, I'm really excited to see how we can apply these methods that can be helpful for my collaborators who are trying to really understand how certain types of heart failures occur. Yeah, so with that, I just want to summarize again, what I'm really keen on is trying to address these challenges that arise because of the heterogeneity and the small data regime in societal level. We are learning from societal data. I didn't quite talk about the query design part today, but that's another aspect that I'm really interested in, is like, how do we go about collecting good quality data? happy to talk about that later. Yeah, with that, thank you everyone. I'm glad to have gotten this chance. Thank you, Tom, for this invitation, and thank you all for your attention. And I'm very happy to take more questions either here or if we are heading out to the library, happy to engage in more discussions.
Because of the season we're in, I'm thinking about politics. Let's say people don't want to admit that they're liberal conservative. And and oftentimes I'll get questionnaires. And you can just tell what answers the questionnaire wants you to say. I mean, that's got to be wordless data, right? More meaningful data would be like, what color is your car? How old were you when your father? How old was your father when you were born? Those are the kinds of data pieces that you would prefer, I suppose, right?
So the thing is that it really depends on what you're trying to learn, right? If a pollster is really interested in trying to gauge, which way people are leaning, unless that is really correlated with the color of the car, then getting color of the car might not be useful for that either, right? Like, so you are asking a really good question. It's really difficult to actually do polling, right? Like, of course, if I assume that when I ask questions, people are going to honestly answer like the questionnaire, yeah, it would be very easy to do polling. But most of the cases, that's not necessarily the case. And it is not because, like, maybe it's not like people are necessarily malicious and they want to give you wrong information. That could be happening. But sometimes people can just be inconsistent in how they're answering. Or it could also be the case that the survey questions were posed in a really bad way. Sometimes that can have an effect on how people answer, right? Like, so there's lots of very challenging questions. Like, we've been doing polling for a really long time, but there's so many things we still don't know how to do that. Yeah.
So I wonder if you could explain how you use profile sensitivity analysis to pre-data collection and post-data collection. Or you're using sensitivity analysis of a circuit, right? Change the resistor 5% and the input versus the output to exist. Can you do that with pre-collected data and post-collected data?
That's an interesting question. So when you say pre-collected data and post-collected data, do you mean like, there's some intervention or something has happened and you want to change, or are you saying about you want to go collect more data later?
So when you're doing a survey, it's a political survey, you ask questions that would when you go down a tree to be pre-selected, and then using the sensitivity analysis, as you referred earlier about garbage in, garbage out. So it is pretty critical to the null hypothesis is to have good data. With sensitivity analysis,
yeah, that's an interesting question, but I don't quite understand in which context you were mentioning that. But it is definitely important to understand how sensitive these methods are for lots of different things, right? For one of them, I was mentioning that how sensitive are they to the sample of the data that I got, right? What if I got a different sample of the data, would I have think concluded something very different? Like, then it would be pretty bad. So we definitely want to understand that it is too sensitive to the sample of the data that we got. We also, a lot of these algorithms that we use in learning processes, these optimization algorithms, they themselves have lots of parameters that needs to be tuned. And so are these algorithms too sensitive to those? That's also something we should, care about. And we make a lot of modeling assumptions, right? So we have some data, we model it mathematically in some way. These models are kind of useful for us to understand what's happening, but we are not generally able to capture everything about the real world in these models. So when we make inferences using these models, it's also important to understand how sensitive are they to the specific assumptions that I made about modeling, right? Like if I slightly, don't obey those assumptions, will I completely change my predictions, or is it that it's still okay, that maybe the predictions will change slightly, but not too much, because that would be like more robust to modeling assumption, for example, right? So yeah, there's definitely sensitivity analysis that, but in lots of different dimensions. Yeah.
Good question. I don't want to sound like a social scientist, but going back to that bias slide, and then you have a valid data set, presumably believable input,
Okay.
consistent input. Now, did the machine learning do better than human or not? And I have two questions. This is the first question. Did the machine learning do better than what traditionally human have done or not?
That's a good question. I'm not quite sure. I don't think in that study they were able to really measure it.
Yeah.
Yeah.
So the second question is that if machine learning wound up with the same problem that humans, which it seems like it made a trouble, at least on a politically, socially correct kind of standpoint. I think more interesting than the output is how machine came up with that function. So that may actually give you better insight as to where the systemic racism, of course, stem from. And it may be not so much the personal preference of skin color, but it may wind up becoming more economic prejudice that winds up getting termed as a systemic racism or educational level prejudice. And I'm just interested in, because machine is deciding what the function is going to be to make that output. If the output is similar to what humans are making, as in the same mistake, then we may be doing things that we don't know, whereas the machine has already told you what the function is in order for the machine learning to spit out that outcome. You see what I'm trying to get?
Yeah. So, but like I'm trying to think. I mean, so there are different things we should keep in mind. One is that I am telling the machine learning algorithm what hypothesis space to search in. So it might find a function that is doing reasonably good job of predicting, but that doesn't necessarily mean that's how the origin is, the actual data generation is happening in like the real setting, right? So we can't, even if you have a good predictor, you can't really claim that that's how actual system is working. So there is a lot of different questions about system identification, but in most of those things, it's like physical systems, right? So it's very difficult to conjecture upon how I might be making decisions, or how you might be making decisions, or how we as humans might be making decisions by just looking at whether these prediction algorithms are able to predict really well. So there is, in the technical terms, there is this question of what is called identifiability, because there could be multiple functions that gives rise to pretty much similar results on the things that we care about, but those functions could be wildly different. So it's not always identifiable. That's one aspect. The second is that many of the modern algorithms, you might have heard of like deep learning, right? Many of these models are so complex that we don't really understand what these models are doing. Like it is a big problem right now, is because we have like these models which have millions and billions of parameters that are getting learned from data that are like really, really large. And when we give it an input and we see an output, we don't know what the machine has done to provide, right? Like, so there is a problem of like actually to explain what the machine did itself is a question, research question of like, how do you explain what the machine did, right? Like, so in a simple thing like that line of like that, example that I showed, that's a very simple example. Very few scenarios might be able to find a nice simple function like that.
So,
Yeah, two levels. One, even if we know the function that we can nicely describe it, we can't still say that that is the actual function that humans are using. So that's one problem. And the second one is that many modern algorithms are black boxes to us. We build them, we train them, we get results out of them, but we don't know what they're doing. Yeah. Yeah, yeah. So it is. Yeah, it is a lot more complicated. Yeah.
But here's a black box.
So, are you saying that
So that actually led really nicely into my question. So if you have a set of unknown data, and I'm just going to use radio signals from space as an example.
Mhm.
If we are looking for intelligent life out there, we don't have anything to train the computers on. We don't have anything to train machines on. If we're setting the machine here to look for intelligent life, look for something different. Is it then possible to query the algorithm to say what is it that you're seeing that differentiates these radio signals from those radios?
I mean, that's a really good question. I think probably domain experts in astrophysics and astrobiology and like other areas on campus might be able to give you a much better answer than I can. So my guess would be that that they might be looking for something like novel. Like what you're asking is how would you know something novel that you've never seen before? That's a really good question. Some of the ways they might be doing it could be that they know what they have seen, so maybe they're trying to identify what is something different from everything they've seen. That could be a possibility, because I'm speculating here because I'm not a domain expert there. The other ways would be that they might have some conjectures or hypotheses on what something should look like. For example, researchers in astrobiology, they have, when they're looking for like signs of life, they have certain conjectures about the quantity of the carbon and like nitrogen and hydrogen and so there could be conjectures on what could be indicating something. So maybe they could be using that. But honestly, like I don't know exactly what they're saying, but good question.
so? Just going back to something you said, millions or billions and billions of inputs, millions and billions of coefficients. Really?
Yeah. So I don't know if you've like seen these like articles that come about like the language GPT-3 that can like generate almost human like language. You can give some prompt and it will generate sentences that look pretty good. Like it can't generate really long lengthy passages. It kind of gets like words with length. But the first few sentences are really good, right? Like it's pretty amazing, like what a lot of these systems can do. But they have like billions of parameters that they are.
So,
Kind of
so are you really learning it? Or are you just hard coding the data?
That's a good question. That's something that we are still trying to understand, right? Like so, because as humans, we don't need like as much examples. There's lots of these algorithms are taking like like a lot of the like software companies have they're coming up with like these language models, these vision models that seem to be doing really, really well, but they have billions or millions of parameters and they're using kind of like scraping essentially all of the internet to really learn these things. So at that point, is it really learning? Like that's a good question. But it is, I think, still nevertheless interesting that that you're able to even generate human-like sentences.
You're trying to use data to get wisdom. Doesn't sound like wisdom.
Yeah, I mean, I think that's it's I think sometimes we like I think there are different questions we might like if my goal is to just get a machine to generate sentences for whatever reason for like that I'm interested in down the line, I might not care about whether I really learned the essence. Like, did I learn this? Like, is this thing really understanding semantics? Is it really understanding? I don't know. But if that's what we care about, then right now it's a question mark, right? So because in just yesterday in the Daily Show, the one of the guests was somebody from OpenAI, and they were talking about this thing called DAL-E, which is it's a system where you can like put a prompt and it will draw something. So you can say an elephant carrying a pan and standing on a football or something, and then it will like generate an image for you like that, right? Like so, that's pretty awesome. But at the same time, it's learned again using insane amounts of data, right? Like so, yeah, I think there's pretty amazing systems out there, but also lots of questions about like what are they really learning? Yeah.
Yeah, I was wondering if you could say something about the amazing improvement in foreign language translating capability. As recently as even 10 or 15 years ago, the results of online or computer translation were laughable. It required quite a bit of editing before they could be used for any legitimate purpose. But nowadays, the quality is incredibly high, and very little editing is needed to be able to use the translations. Could you discuss that a little bit? Thanks.
Yeah, I can. That's a really good point. So again, my research focus is not natural language processing, so I might be able to give you very high level, like what I understand from it. So a lot of that progress has come from again data, right? So literally using like lots of like translated works, lots of like transcripts. I think in like places like UN, you have like the same thing that is like transcribed into multiple languages, and books like I think probably Bible is the one book that is translated in like lots of different languages, and there's like so you can get like a lot of like the data, and then this data to kind of that's what has really that's one thing, and the second thing is the computing ability, right? Even if I have lots of data, if I don't have computers that are capable of using that data to learn, because you have now a gigantic optimization problem. And if I don't have the computational power to do it, then it would be of no use, right? So, so these machines like really have become like much better in terms of like there's these things called graphical processing units, GPUs, so which are being leveraged a lot for a lot of these machine learning algorithms. And I think it's a combination of a lot of compute power and lots of data that have together made this possible. But again, going back to that question of like, if we are getting philosophical in terms of understanding, like, is it really learning? Is it like really getting the core or the essence of like, is it learning like we learn and things like that? That we don't know. But we are building machines that are capable of this. And another reason why I think in the last 5 to 10 years, it's mostly companies which are able to come up with these models. Because it's incredibly expensive to train these things. Like the machines themselves cost a lot, like the data, it's a lot of, So sometimes like with the machines that are, in the labs have in universities, sometimes, it is difficult to even load the model. That there are so many parameters that it is very difficult to even load the model, let alone train the model, right? Like, so, yeah, I guess I don't know if my answer really answered your question, but yeah, we are at a stage where we definitely have pretty good machine translation systems, pretty good image recognition systems, pretty good kind of language generation systems. But there are lots of caveats still. For example, a lot of the image recognition systems, right? So if you get images from, many of them are trained on images, a lot of images that came from people have uploaded, there's a skew in which parts of the world many of those images have come from. So these systems can sometimes fail if you have images from like, different countries and like cultural contexts, and they can completely not know what to do. Yeah.
Thank you very much. Appreciate it.
Yeah, thank you, everyone.
We haven't done here, we do go across the library, it's far, but yes, the library. Continue the conversation, that would be great.